Hello, everyone, and welcome to another episode of the Marine Conservation Happy Hour. And you can see our guest here today is Dr. Joellen Russell, who's a distinguished professor of oceanography at the University of Arizona. Ironically, a professor of oceanography in a desert state of all places. And we're going to be talking about the ocean carbon cycle and some of the really, really cool research that's going on there at the moment. But first of all, introducing my co-host, Dr. Scarlett Smash. How are you doing, Scarlett?
I'm doing fantastic. Oh my God, she has me so jazzed up. We were talking a whole bunch before this, and I am just ready for more. I need more of her.
We really need this to be like an hour long to cover.
We should
even
have been
half
friends
the
a
things
long time ago.
I was thinking the same thing.
But today we're going to be talking about the ocean carbon cycle and the importance of that is for climate change. But before we do that, Joellen, can you tell us about how you got to where you are today? So you're a distinguished professor. What's your story? How did you get there?
Well, I have my dream job, quite literally my dream job. I've wanted to be an oceanographer and a professor since I was 11. I wrote scripts or bust on my chucks on the white walls, on the side of your sneakers when I was little. And I grew up in an Alaskan fishing village above the Arctic Circle on the Chukchi Sea, which is part of the Arctic Ocean. And I have been headed here ever since. So I went to, I wanted to go to Scripps for my graduate work. My great aunt, Mary Ellen, who is an engineer at the University of Washington, said, "You've got to go to Scripps. If you want to be an oceanographer, it's the best place in the world. You've got to go there." Now, she's a West Coaster, so sorry, Woods Hole. We know there are other good places, but the only one that anybody ever talked about to me was Scripps. So that's where I wanted to go. And I was heartbroken to find out that that was a graduate program and I couldn't go there for my undergrad. I was just like, oh no. So I went to my backup school. I went to Harvard, and that was fine. But I eventually got to Scripps. And then, now I'm an ocean, and they let me go to sea my very first year. And I went to the Southern Ocean around Antarctica, where and I grew up with blizzards, right? I grew up with, full on crazy ocean weather and the waves and the wind. And I had never seen anything like it when I got to the Southern Ocean. The waves were so mountains of water falling on the ship, black water over the bridge. It was crazy. And I thought, what is going on here? I don't see this in my textbooks. What is going on here? Turns out there's the world's largest current with the world's biggest winds. The westerlies are 30% stronger around the Southern Ocean than they are in the Arctic. And in addition, we've got the Antarctic Circumpolar Current, which carries 178 million cubic meters of water a second, which to most people doesn't mean anything. But the second largest current on Earth is the Gulf Stream, and it only carries 40 million. Which is like less than a quarter the size. So I was hooked. I've been hooked ever since. And I'm still working on that.
Phenomenal. We'll talk a little bit about some of the Southern Ocean research that you've been working on in a moment. But let's talk about the ocean carbon cycle, because that's really, really important. But so few people really know about it. So can you explain what the ocean carbon cycle is? I know people who think it means pieces of coal floating around in the ocean, but it's not. And what is the ocean carbon cycle and why is it so important?
Well, the important part is easy, because 1 out of 4 molecules of carbon that comes out of anybody's tailpipe when they drive their car, if it's not an electric car, if it's burning gas, 1 out of 4 molecules of carbon out of anybody's tailpipe anywhere in the world, any kind of burning, goes into the ocean within a year. Yeah. And 1 out of 8 goes into the ocean around Antarctica, goes into the Southern Ocean. And that making it, half of the global ocean, our carbon uptake goes in around that very cold, very wild ocean around Antarctica. So that's why it's so important, is that it's 1 out of 4 of all the burning we do, right, is going into the ocean. And how much it goes in, there's another reason, which is that of all the active carbon in the world, only a fraction is actually in the atmosphere. Most of it, everybody's like, is in the trees. I'm like, no, not even close. Most of it is in the deep ocean. It's the rot of ages. It's basically the poop and dead bodies of 1,000 years that have rotted and been turned back into the organic plant food, et cetera, by the bacteria, by the microbes in the ocean. So they all died, they sank down, and then they were eaten by the bacteria, who then respired them back into their original components. And it's sitting in our deep ocean, circulating with the ocean. So as our circulation of our ocean changes, we are taking up 1 out of 4, but there's so much carbon in the deep ocean that if we actually mix that up to the surface, we might actually degas carbon to the atmosphere still, even under our human-made carbon-rich atmosphere, even now. We live on such a beautiful planet. And that carbon cycle is so important, because that carbon pollution blanket that's wrapping around our planet today and keeps going up and up and up and up is responsible for this massive energy imbalance. And here's the second role of the ocean and climate. There's the carbon cycle part, which is absolutely critical, 1 out of 4, but there's also the heat. So that carbon pollution blanket that wraps around, we have IRBE, the Earth's Radiation Budget Experiment, looks out of the sun and in at the Earth and says, hey, about the same is coming in every year, but less is getting out. So it means that we must be warming. So everybody's like, well, but it doesn't warm in the atmosphere every year. I mean, we've had a lot of hot years lately, but it's not every year hotter. So how can that be? Yeah, because that's only 3% of that energy imbalance is hanging out in our atmosphere, making us hot here in Arizona, roasting. Most of it, 93%, has been absorbed by our ocean. Our ocean is our global air conditioner. It's what's keeping us from catastrophic warming already. So taking up 93% of the heat and 25% of the carbon, and basically providing food, protein, and livelihoods for 3.4 billion of our 7 billion plus people on the planet. So our oceans are really important. And that carbon cycle piece is both very important for how much it's taking up now, and also a huge worry, because they've got that chemistry, that massive amount of carbon sitting just below. It worries me.
So we were talking before this podcast started recording. The oceans, vital to life on this planet, vital to supporting climate, vital as a food supply. And how many oceanographers are there in the entire world?
Everybody, we are the thinnest of thin blue lines that you can imagine, because of course, according to the American Geophysical Union and the European Geophysical Union, there are roughly 6,000 PhD level research oceanographers in the world. Out of 7+ billion people, we have 6,000 human beings who are responsible for 72% of the Earth's surface, 3.4 billion people's food and livelihood, 93% of the energy imbalance, and 1 out of 4 carbon molecules that comes out of anybody's tailpipe. And there's only 6,000 of us.
So you're more likely to be an Elvis impersonator than an oceanographer.
Exactly. Oh, you can't imagine the conversations I have on board airplanes. I mean, pre-pandemic, of course, but I'd sit down and they say, well, hello, what do you do? I'd say, I'm an oceanographer. What is that? I know. So 60,000 meteorologists here in the US, 600,000 geoscientists, but only 6,000 oceanographers. What are we going to do on the day that the president comes to us and says, hello, oceanographers, we need 10,000 of you, chop, chop. Be like, well, if we really pushed, we could maybe make 500 in 5 years. Would that do? No? 10,000, you say? Well, I think every every geology department in the country probably needs a few more, right? We need to get this teaching going. it's a big deal. We are behind the 8 ball given the absolute critical importance. We're also in the middle of the United Nations Decade of the Ocean with our sustainable development goals that we're all working on together. I mean, we want to live on a sustainable planet. 72% of the Earth's surface being this lovely ocean commons that we share. So this is critical research. It's also important. I mean, so my job as a research scientist is to supercomputers, robot floats, and satellites, right? I use everything in the kitchen sink to get a look at how our ocean is changing, how the carbon uptake is changing, how the circulation is changing, those currents, are they getting bigger, stronger? The answer is yes. But also it's to train young ones, launch those kids, and to get our citizens better understanding just how critical our oceans are to us. Here in the middle of our desert, in my current intro oceanography class, we have over 550 students. Yeah, that's just the fall section. Wait till spring. I know, because it's very popular. But we are kind of, if we were thinking about this as a war effort, boy, are we behind in the recruiting.
Oh, definitely. You mentioned there robot floats. Now we have to talk about this because one of the problems with oceanography, it's really expensive normally, because those big ocean going vessels, particularly going to somewhere like the Southern Ocean with those huge waves, you need a big ship. And you can only cover a very small sliver of the ocean. So tell us about the robotic floats.
That's it. You're absolutely right. And not only that, but it takes forever to get where you're going. You could be 14 days transit just to get to your research area. This has happened to me. My longest cruise is 56 days, but I've been out for 49, and other, they're long because you have to go a long way to get out to the middle of nowhere in the Southern Ocean. And you know why it's so important. So what we've been working, I knew this when I was in grad school, and have been working with colleagues to try and figure out what can we do? If a ship costs, bare boat, 50 grand a day, right? Just the boat. And so in 2 days, $100,000, you can do about 5 profiles all the way to the bottom and back up, where you drag the water up, take subsamples out of these big bottles of water, and then and that's your, therefore get an idea of what the water was doing. That 5 profiles every 2 days. Now, one of these robot floats, it will do 250 profiles, right? For the same $100,000 or less. And it will do it without us being there. No people. Every time, it'll basically sit at 1,000 meters, which is about 10 football fields down. It'll drop down to 20 football fields down, 2,000 meters, and it'll make a continuous profile of measurements to the surface, and then it'll beam that data back by Iridium satellite. And we'll post it online for the entire world to see within 2 hours with just a quality control algorithm that's applied. It's amazing. Now, the Argo fleet, and that's the original temperature, salinity, pressure floats, there are thousands of these out. Those are cheaper. They're like in the 20 to 30 grand range. Mine tend to be those more expensive ones. Me and my colleagues have been working on these biogeochemically censored floats. What we mean is basically ocean health. We're looking at the oxygen content, the pH of the water, which is, acidifying slowly. We look at the nitrate, which is the plant food in the water, as well as looking at like chlorophyll for optical sensors, meaning how much is growing, and how much of that particulate matter, the poop and dead bodies, is kind of coming down through the water column. And we can do all of that in addition to the temperature, salinity, and pressure that you would normally get on a float. And we have hundreds of these out now. And the National Science Foundation, first they funded our regional array, which was just for the Southern Ocean. It's called SOCOM, the Southern Ocean Carbon and Climate Observations and Modeling. And then they just last October, they funded GoBGC, which is a mid-scale research infrastructure project, not just to do my favorite Southern Ocean, but the whole world. We're going to watch ocean health in near real time for the first time in human history. Every time before this, we had satellites and they could look at the surface, right? But if you wanted to see how our ocean was evolving, how the ecosystems were changing, the pH was changing, what was our human impact, how are the currents moving? If you wanted to see this, you needed to sit out on a ship. Now we sit on a ship and we calibrate our floats, and then we go home and our floats stay behind and they work under the ice. And that's the coolest couple of lines of software that make them ice avoiding. We thought we were going to have to put really fancy infrastructure and equipment on them. And instead it's 2 lines of code out of people from Steve Reiser's lab at the University of Washington. 2 lines, best lines ever. Hey, dummy, if your temperature sensor starts changing really fast, go back down. And it's true, and it works. And so we've had them popping up in these gaps in the sea ice called polynyas, and actually coming out in the slushy ice when it's not, too hard. And so we're getting all this data from under the ice around Antarctica, from all over the Southern Ocean. And now they're deploying for the rest of the world so that we can finally do real-time carbon accounting for the ocean, which is something that everybody needs to know. Because if we know our atmosphere and we know our ocean, who's left? Individual land masses owned by individual countries. So we can actually finally, it's like tagging all the sheep on our global commons. We'll finally know who's grazing too many sheep on our commons. Before, all the carbon atoms were kind of the same, and some were going to the ocean, some were going out of somebody's tailpipe. How could you tell? We're going to be able to do this, and we can do it with robot floats. Just by the way, there's also a really cool law of the sea thing that is really interesting. If you drive something into somebody else's ocean exclusive economic zone, if you have an AUV, everybody's like, why not an AUV? We could drive them. They'd be awesome. I'm like, yeah, but they're more expensive and they require people, right, to drive them, which my float just does all its business by itself. Doesn't need any help from me. Yay. But what is awesome about this is the law of the sea says if it drifts in, it's legal. And the International Oceanographic Commission has approved our sensors. It's a UN commission, United Nations Commission on Oceanography. And they've agreed that our sensors are approved. And so we can now deploy worldwide to get a global look at our ocean carbon cycle. Can you imagine? No one in the history of the world has ever had an idea of how our ocean breathes. And now we can see it.
This is a really exciting type of technology, and there's lots of potential for growth and additional sensors.
Oh, you're so right. Woo!
Put acoustic tags on them and listen to all the whales around the world as well, and all sorts of things. And one of the neat things about this latest project, the Go BGC, the new types of floats, you can actually adopt a float. I know there are high schools that have adopted floats and they've painted them with logos on the side and then dropped them in the ocean. So they have their own, like the Frolston Flyer or the Brighton Bobber going around the ocean.
As oceanographers in SOCOM, we like to try and get more people looking at the ocean, right? So we agreed to put logos on any float that was adopted by students, classrooms, people, individuals, etc. And we set up this program called Adopt a Float, which has now been expanded to Go BGC. So my float is the Woohoo Golden Dragon float.
Yes, Queen.
Do you think we could
have a dragon?
Do you think we could get a marine conservation happy hour float?
Oh yes.
Oh, I'm ready. I'm ready.
Have a logo?
Oh yeah, totally. I'll definitely do that. Well,
I have a float. You should have one too.
Yes, I think so too. This is such a big hot topic about like carbon sequestration, capturing carbon. This has been, I'm so glad that everyone's starting to know what this means, what's the importance of this. So my question to you is like your big take home like messages, like what we can do. Why is it so important? Like, and what's so interesting is I've listened to a few of your speeches before.
Aww.
And one of them really got me, where it was like, this is our technical war. This is this is the big thing that we need to be overcoming and take control over and fight. And
Yes.
so I'm just wondering what your take home message is for us.
Well, to be honest, that challenge was not for me. I'm just repeating it. That challenge was from Walter Munk, world's most famous oceanographer, beloved Scripps oceanographer, right? And he worked for the Defense Department during World War II. He was put on the wave equations. And the story goes that he was the last call that Eisenhower made before he said go on D-Day. That's why he's so famous, not just because he's done extraordinary science since then, but in an hour of absolute need where we had needed to understand. So you needed bad weather and low cloud covers to keep the Luftwaffe off the landing fleets. But you also meant that there would be higher waves, and the gunnels were very low on the landing boats. And at 5 feet, they would come right in, no problem. But at 6 feet, they would turn into the waves and they would swamp. And with all the heavy packs, they would drown. Our soldiers would drown. And so Walter was working on this project. And of course, it worked, right? So he was standing at the Ocean Sciences meeting before he died. And he... God, it chokes me up because he's right. He stood there, an old man, and he said, Hitler was my generation's great challenge, and climate change is yours. You must hold the line. I know there aren't enough of you. I know you're worried that no help is coming, but help will come. But you need to keep working. You cannot fail. You could have heard a pin drop. Maybe a third of all the ocean, there was like 2,000 people in the room, maybe a third of all the oceanographers in the world were right there for this plenary at the Ocean Sciences meeting. We won't. We are not less determined than our grandparents. We are not less clever and innovative. We will figure out where all that carbon's going in real time. We will do our carbon accounting so that everybody understands the impact they're having on our global atmosphere and the consequences that there will be for our children and grandchildren. So yes, we've got robot floats, we've got supercomputers, we've got satellites, but there are too few. And frankly, it wouldn't hurt to have a plus up in the budget, because with this few of us, even if our hardware is expensive, we have 72% of the Earth's surface, 93% of the energy budget, 1 out of 4 carbon molecules, food and livelihoods for 3.4 billion people. And our line is too thin.
Well, that's an amazing final message for this particular episode. I don't think we can cap that. So thank you very, very much, Joellen, for joining us. And thank you for everyone out there who's either watching this on the live stream, watching this on YouTube, or tuning in on the podcast. Thank you very much, Dr. Scarlett Smash, and happy conservation, everyone.
Happy conservation. Thank you for having me. Bye-bye.